This is a video about getting LLMs to correct themselves, and more specifically about how to train a large language model using a technique called rejection sampling to get it to correct itself and therefore improve its accuracy overall. So I'm going to call this verifiable backtracking. Please let me know if there are any other related papers on this I'd be interested to read. I am actually going to start by reviewing a paper called S1, which is about simple scaling of LLMs. And this paper uses a technique called budget forcing, which basically gets a model to think for longer. And we'll see how this is related to the ideas I'll talk about today around training a model to backtrack on its answer. So let's start off by describing what is backtracking. And before describing that, I need to answer the question of how do models think? And specifically here, I mean reasoning models. So I mean, for example, a model like, say, DeepSeek R1, where it will have a question. Let's say the question is something like, what is 3 plus 3 plus 3? And the answer will be provided like this. So it will start off usually with some kind of think tags or maybe reasoning tags. So it will think and say, well, 3 plus 3 is 6 and 6 plus 6 is 9. And then close the think tag and then give the final answer here, which is going to be 9. So this is an example of DeepSeek R1 and how it does thinking. And notice how there's this section here, which often can be quite long, and the model might decide to go back, correct itself, different reasoning logic before finally giving its answer here in final form. Now, if you have a model that's answering like this, there's an idea, and the idea is when it generates this think tag here, you can actually cause it to delay its answer and to think for longer. So if we say getting a model to think for longer, what we can do is we can get an answer like this here. So I'll just copy this answer. But when the language model responds with this think tag here, rather than creating more tokens, we suppress this think tag and we replace it by saying something like wait, ... And if we do that, the model is going to continue to reason here. So the model is going to give some more lines of reasoning before eventually then closing its think tag and giving a final answer, which, hopefully is still the correct final answer. So one of the key ideas here, which is called budget forcing in the S1 paper is, well, actually, you can decide how long the model is thinking simply by suppressing the think tag and replacing with some phrase like wait and getting it to think for longer. And sometimes it will already have the right answer, like 9, and you hope that by adding the extra thinking, it's not going to give a wrong answer. But sometimes it might have the wrong answer, and maybe by adding the thinking, you get to a better right answer. And so the question is, if you do this, and all you're doing is you're setting a max length for the thinking here and making sure the model reaches it. And by the way, you can also do the opposite so that if the model is not finished thinking, when you reach a critical number of tokens, you can just force put in a think tag like this and force it then it's going to give its final answer like this. You might even encourage it by saying, and therefore my final assessment is ... And you can basically force it to give an answer in that way. So this is budget forcing, and it doesn't require any knowledge of whether the answer in advance is correct or not. You're simply getting it to produce a certain amount of fixed thinking tokens. And you can see that in this paper, simple test time scaling. And you can see it in this chart here, where we can see the amount of forcing that's happening. And the average thinking time here is being increased. So it's ignoring the end of thinking, 2x, 4x, 6x. And so this is saying it's going to replace that closing tags 2 times, 4 times, or 6 times to force the answers to get longer and longer. And it turns out this does improve accuracy. And of course, this isn't coming for free, this accuracy, because you need to generate more tokens. And it's even worse than that because the cost of those tokens goes up kind of quadratically, or at least the cost of the completion goes up quadratically, because every new token now has to read back to a longer sequence before it. So you have this quadratic increase in compute for your completion length as you try to add tokens. So it's not coming for free. And one of the key questions is it better than just doing parallel scaling via majority voting? And here you can see, and this doesn't take into account the quadratic consideration I just mentioned. It just looks at on a per token basis, which is a linearized version, which will favor the sequential actually. But you can see if you do look at it on that basis, the sequential forcing does look to outperform this kind of parallel scaling. And it would be interesting to do this on the basis of flops to see if on a flops basis, one approach seems to do better than the other or not. All else being equal, which probably that's not the right way to look at it. What way should I say? It's interesting, regardless of whether this ends up being economically better, it's certainly interesting that if you just force the model to think for longer by appending or taking away these closing think tokens, it's interesting that you're able to get to better answers. So I'm going to do a variant of this for doing what I call verifiable backtracking. So in the case of verifiable backtracking, and I'll start up a new section here, what we're trying to do is we're trying to get the model to correct wrong answers, but we're trying to do it via a training approach. And the way I'm going to do this is via sampling. So for sampling, I'll have a question like, what is the capital of France? And then I'm going to sample 8 answers. And the 8 answers might be something like Paris, London. Let's just do 3 actually. There's no need to do 8. And in this case here, we've got 1 correct answer and we've 2 incorrect. Now, because I know through this sampling, and remember I'm in training, I'm not at inference time, because I know which ones are wrong, I'm actually able to get the language model to correct itself in the case of those answers. Okay, so let's look now at verifiable backtracking, which is kind of a related idea, but it happens during training time. So this idea of budget forcing, this is a test, it's an inference time approach where you're forcing the model to generate a certain length of completion. I'm now interested in training and how can I get the model to improve its backtrack during training. So let's look at a question here and let's look at, again, what is 3 plus 3 plus 3? And let's look at a potential answer. I'll just look at the same answer here, but this time I'm going to consider sampling an answer where it is wrong. So I'll say 6 plus 6 is 8. Okay. Now let's consider sampling another answer. So I've got a first answer and I've got a second answer. And in the second answer case, let's just say, the first answer, the final answer is 8. And in the other case here, let's put in second answer of think, and we'll put in, 3 plus 3 is 6 and it's a 9. So we're going to put in the correct answer here. So what I've done is I've got a question and I've got 2 answers. My goal is to generate correct answers that I can use for supervised fine tuning. So I should write that down here. Goal is to create correct answers for supervised fine tuning. Okay. So I sample my question 2 times. I probably would sample it more, maybe 8 times in practice, and I get some answers. And what I do now is I look through the answers. So the second answer is good. So I'm going to take all of this answer and I'm going to use this answer for fine tuning. So I'm going to use, I'll just say use the above correct answer for supervised fine tuning. And I'll say second because it's correct. But in the first case, it's incorrect. So what I'm going to do is I'm actually going to send the first answer back for more completion. And the way I'm going to send it back is I'm going to take all of this portion of the answer. So I'm going to set my completion. I'm going to start the assistant response like this with the thinking tags. And I'm going to insert here something like wait. I'll just say wait. And if I insert it like that, the model is naturally going to start completing. And as a response to that, it should start saying something like, wait, oh, I realize that's incorrect. Those numbers sum to 9. And then close the think tag. And then it might say something like, final answer is 9. Okay. So you can see here, if I sample answers from a question, and I sample ones that are wrong, I can detect they are wrong just by verifying them, and I can send them back in, remove the think tag from the incorrect answer and remove the answer, and just get it to complete some more and put in this little phrase here, wait, to encourage it to do that. And if I do this, I'm going to have a data set at the end that's going to have correct answers. And it's also going to have answers that were not correct on the first go around, but were correct on the second go around. Now, not all of the times that I send back the question with a partially completed answer will it be corrected. Many times it won't be, but in many cases it will be, or at least in some cases. So I'm going to increase the number of correct answers I have from my rejection sampling process. And I'm going to include some samples where there's this kind of wait phrase contained within it. So I'm going to show you how I did that in code. And this is drawing on the same sample generation script that I use in the reinforcement learning videos I've made recently. And in these videos, I'm trying to train a small llama model on a maths dataset, grade school maths, which is an 8K dataset. And the way I do that is by generating high quality data by taking 8 samples per training question. And now by adding in this weight parameter here, what I'm allowing the model to do is when it generates an incorrect answer, it's allowed to go back and regenerate by continuing on with that weight ... Now there's a little further nuance here, or rather an improvement I can make, which is with the exact phrase that I use. So I've talked about using the phrase wait. And if I do a small ablation just on 100 test rows, what I find is that when I sample 8 times per question, which is 800 questions, there are 8 questions that end up being corrected by wait. So that's a quite small percentage. But I can increase that somewhat meaningfully by being stronger in the little phrase I add in. Because I know the answer for sure is wrong, I can actually say, hold on a second, that's wrong. Let me think through this again. Or some other statement like, that's definitely wrong, or that's completely wrong, or I realize now that is wrong. If I just say wait, it's a bit more vague. And so the language model is less likely in its generations to actually change its answer. So yeah, just by having a more forcing wait phrase here, I'm able to improve the number of answers that are fixed by just going through a second iteration. So let's take a quick look at the script. And I want to in particular look at what happens when we pass in this wait flag. You can see it's one of the arguments. And this is waiting for server to be ready, which is unrelated. So where we can see the wait functionality implemented is in the processing of questions. And within processing questions, we're processing a single question. And within that, we are getting an answer. So we're first making a call to get a model answer. I know I'm moving quickly through this because it's in a previous video, but I have a function that gets an answer. And then for each answer, I check the result. And if I get the result is incorrect, and I also have the waiting enabled, then I'm going to extract a partial response. And what this means is I'm extracting all the way up to the closing think tag, and then I do a retry here. So let's take a quick look at extracting the partial response. Function is defined here, and what it does is extract the response up to the think tag, and it adds in, hold on a second, that's wrong, let me think through this again. So you can see here, it's finding the position of the closing think tag, it's getting everything up to that point, and then it's returning that partial response with, hold on a second, that's wrong, let me think through this again. And so now I'm able to sample data in 2 ways. I can sample it just by taking 8 samples per question, but I can also take 8 samples per question, and for everyone that's wrong, only the first time it's wrong, it gets sent back with this partial response, encouraging it to fix the answer. And when you do this, you're going to get some rows of data that are going to have answers that basically have been fixed. And so I roll that out on 1000 rows, and I'll show you the script here. I run the sampling on the GSM-8K dataset. I run it on the 1B unslot model, 1B Llama 3.2 model for generating the 8 samples. And I run it on the full training set here with wait. Now, this think tags flag here makes that I'm enforcing the format. So I'm also only filtering out samples that have got the correct reasoning format. If the reasoning format is bad, I'm going to throw away those answers and I'm not going to consider them for the purpose of using later in my supervised fine tuning. So I run through that script there and generate the samples. And just to show you the difference, I've run it in two ways. I've run it with and without the weight. So I can go to my results, I can go to the base model, and I can look at the data set here that is generated with weight and without weight. So without weight, I've got about 85% correct on a pass at K basis, 32 at a majority at K basis. And then when I add in the weight, and this is my training set, I get 88 instead of 85. And actually my majority at K is pretty much similar. But from a training data standpoint, what matters actually is the pass at K, because that means that I reach correct answers, and any correct answer I reach means I have an extra answer to put in my training data set. So the improvement in the pass at K here on the training data set means I've got more training examples available because of this weight type performance. Now, one nuance point here is that because I'm allowing essentially every answer to have a second go, as a limit, you can think of this as sampling twice as many points. So there is a cost to it. I need to sample at maximum twice as many points, assuming they were all wrong in the first go. Of course, they aren't all wrong, so it's less than twice as many samples. But one useful way to think about this is how much do I improve performance when I allow for a retry versus when I just sample twice as many in the first place. And that's something I'll talk a bit about later as well. So I have my data now that's augmented with these samples that have been self-corrected. And I know that the ones that have been self-corrected are correct because, first of all, I verified it was wrong when I had to retry it, and I verified it's correct when it did retry, and I filtered out everything else. So I know for sure, I verified for sure that these are correctly backtracking. Now, maybe there are other logic errors within the answer, but broadly, the answer will initially have a wrong part, and then it will be corrected, and then it will have a correct part. So I take those answers and I do supervised fine tuning on them. I actually first just create some pairs of data. You could do ORPO training. I actually do supervised fine tuning, which is done using this supervised fine tuning script here that I explained in an earlier reinforcement learning video. And I do it on the full data set, which turns out to be a data set still of roughly 14 to 15,000 rows. And I run it for one epoch at a constant learning rate. And then I run an evaluation on the eval set, which is about 1,000 rows in size, 1,319, to see the performance. So the question now is, how does this compare in terms of performance on the eval set compared to the baseline if I just train on a data set without weight? And what you can see is the trained model yields a result of about 84%. And this is compared to a baseline, which is about baseline is about 80%. And the majority at K gets to 40% compared to a baseline of about, it's 32%, 35% if you scroll up. So I'm finding that you can train the model in order to backtrack and get an improvement both in pass at 8 and majority at 8 by using this technique. And this is pretty interesting because when I just do rejection sampling on its own, and I do that for multiple iterations, I haven't been able to get over 80% roughly in terms of pass at 8. So this is the highest score I've been able to get, and it's only been achieved by doing this verifiable backtracking. Now, this doesn't come for free. Because you're allowing for backtracking, it means that your responses on average are a bit longer. Actually, the response, I measured it here. I find that for about a 12.5% increase in pass at K, I see an increase in response length of roughly maybe about 10%, 10.3 is too accurate to say. So roughly speaking, I'm seeing kind of a similar increase in response length versus the pass at 8 performance. But still, this is pretty interesting because if you have an answer that's been given in series, you don't need to have a verifier. You can allow people to read from the final answer. Whereas if you sample them in parallel, either you need to do a majority check or you need to have some kind of a verifier. And basically this is a choice between, do you want your model to be sampling in series and make longer answers, or do you want your model to be sampling in parallel? And what we can see from, say, the O series of models like O1 or O3 or from OR1 is that there's a benefit, or at least those companies have found it useful to encourage models to sample in series, whether that kind of emerges naturally through reinforcement learning or it's elicited in these kind of verified retry approaches, it's beneficial to do it in series because you know that the final answer is what the user is going to rely on, and you don't need to introduce a verifier to then pick between your parallel samples. So that's my simple demo. Hopefully you can see the high level idea, which is that you check if the answers are right or wrong. If they're right, you save them for training. If they're wrong, you let them retry by taking away the think tag. And then you regenerate once. You could regenerate multiple times, and you keep again only the correct answers. And I'll note that when you look at the training set, or rather the inference set, so let's look at the inference set on the trained model. I need to find the model that's been trained with weight, which I've used the number 99 for. And you can see here, if we check out the final results and look at all inference results, I just want to show you that if I look for this phrase, hold on a second, it's not the case that the model will always get the correct answer. You can see here, it does kind of backtrack and get the wrong answer. In fact, it tries to backtrack in quite a lot of cases, but you'll find that it does sometimes, like in this case here, it is reaching a true answer by doing the backtracking. So to be clear, in the training examples, we're always correctly backtracking because it's verified, but at test time, you find that it will backtrack in cases where it doesn't correct. It will also sometimes backtrack multiple times within the same answer, which is an interesting kind of emergent behavior. You can see multiple uses of hold on a second within the same answer. Let's see if we can find one of those. So here we just have one. It's just holding on a second once. So here you can see it's saying hold on a second twice within the same answer, although it's hold on, that's wrong too the second time. And it does manage to get out to a correct answer afterwards. So there is some interesting emerging behavior here. And yeah, if you extend this approach, it seems, and I wouldn't say this too confidently because I would need to rerun my tests more times, even though I did a large test split. You just want to be sure to say anything for 100%. But it seems that this is a way to improve performance of pass at K, which is interesting because it's not easy to improve pass at K. And second of all, you can see that by extending on this kind of approach, you can probably, and the second interesting thing is that you can use this kind of approach to get models to produce longer and longer answers and effectively get them to sample in series, which doesn't require a verifier, rather than sampling in parallel, which is a bit more academic. So that's the overview. You can find the scripts. They're part of the advanced fine-tuning repo over on trellis.com if you'd like to purchase a lifetime membership. In the meantime, let me know any comments below. Cheers, folks.